So, welcome friends to our last session of this course. In the previous session we have started our discussion on the time optimal control system, and we have seen that for a linear time invariant system x dot t equal to axt plus but, in which my u is bounded as mod of ut is less than or equal to 1, we can define our Hamiltonian as h 1 plus lambda prime t axt plus b ut. We got our state and the co-state equation. Co-state equation is lambda dot t as minus a prime t lambda star t. So, this means this equation can directly be solved in terms of the lambda t, and the Pontryagin minimum principle we have applied as my Hamiltonian 1 plus axt lambda dot t plus u prime t must be less than or equal to a journal value of the u. If u is as u star and u is the journal value of the u, so this will be less than this, and we have shown that this can be minimized by selecting the u as plus 1 or minus 1 depending upon the value of the qt, and qt is nothing but our b transpose lambda t. So, this b transpose lambda t will decide my switching value q from 0 to 1, and we have shown that my system should be completely controllable. This means no singular time optimal control system can be controlled for minimum time, because here the u is undetermined between the period t1 and t2. In the next we will see the application of a time optimal control system to a double integral system, and if you will model the double integral system in state space, it can be represented as x dot t equal to 0 0 0 1 xt 0 1 ut. So, by this we can define a double integral system. U is bounded as less than or equal to 1. So, if we will first check the controllability of the system, you can try yourself, then it shows my system is completely controllable, because to check the controllability we have the controllability matrix B AB for this system. My B is 0 1 and AB will be, A is 0 1 0 0 and B is 0 1. So, what we will get 1 and 0. So, this is 1 0 and the rank of QC is, it is clear from this is equal to 2. So, AB pair is controllable. So, it is simple to show my AB is controllable. This means I can apply the time optimal control solution to this problem. So, as a first step I will write my Hamiltonian as 1 plus lambda prime axt plus but, and if I will write the value of a and b, so my h will comes out to be 1 plus lambda 1 t x2 t plus lambda 2 t ut. Objective is to minimize this Hamiltonian. This means I have to check the value of lambda 2 t. It should be, if lambda 2 t is negative, u will be positive. If lambda 2 t is positive, u will be negative. So, this means I can decide my ut as the signum function of lambda 2 t, because the sign of lambda 2 will decide the sign of my u. If this is positive, u will be negative, and if this is negative, u will be positive. So, these are, I have lambda 1 t as del h by del x1, means this is my co-state equation, this is equal to 0. This means I am writing my lambda 1 dot t as del h by del x1 with negative sign, and what is my h? If you will see, my h is 1 plus lambda 1 t x2 plus lambda 2 t ut. So, this is h is not a function of x1. So, this means my lambda 1 t will be 0. This implies the solution of this is lambda t is lambda 1 t is nothing but lambda 1 0, where lambda 1 0 is my initial value of the lambda 1. Similarly, my lambda 2 dot t is minus del h by del x2 . This implies my lambda 2 dot t is what? Means del h by del x2. So, this is nothing but lambda 1 t. So, this is nothing but my lambda 1 t, which is nothing but my lambda 1 0. So, if I will write the solution of this is lambda 2 dot t, which will be this is negative sign. So, this will be negative, this will be negative. So, minus lambda 1 0 t plus lambda 2 0 will be the solution of. So, this is the solution of lambda 2 and this is the solution of my lambda 1. So, this we are representing here. My lambda 1 t solution is lambda 1 0 and lambda 2 solution is lambda 2 0 minus lambda 1 0 t. So, means now we have to decide what should be the value of switching. What is my control law? Control law is ut equal to minus signum of lambda 2 t. This means we have decided my optimal control as signum function of lambda 2 t. This means lambda 1 0 t with negative sign plus lambda 2 0. So, what the switching point will depend what is the value of lambda 1 0 and lambda 2 0. So, now depending upon the initial condition of lambda, my these two equations means lambda 1 t equal to lambda 1 0 and lambda 2 t equal to lambda 2 0 minus lambda 1 0 t. So, my ut is nothing but the signum function of lambda 2 t, which can be written as minus lambda 1 0 t plus lambda 2 0 t. So, based on the initial value of lambda 1 and lambda 2, we can define the switching. See, lambda 1 is greater than 0, lambda 2 is less than 0, means lambda 2 is negative. If lambda 2 is negative, lambda 1 is positive. So, this means the whole term will be negative. So, my u always will be positive in this case. So, if my initial condition exists in this way, my u always will be positive. The second case, if you will see, lambda 1 0 is less than 0 and lambda 2 0 is greater than 0, means lambda 2 is positive. In this case, lambda 1 is negative. If lambda 1 0 will be negative, so my this term will be positive and the whole term will be positive. So, lambda 2 t always remain positive in this case. So, u will be always negative. Another is if lambda 1 0 is less than 0 and lambda 2 0 is also negative. So, what we are saying, lambda 1 is negative, lambda 2 is also negative. So, my this term will be negative, this term will be because this is negative, so this will be positive. So, this is a line with positive slope. So, my lambda 2t will be a positive slope. So, initially at t equal to 0, if I will see my lambda 1 is, lambda 2 is negative, lambda 1 is, lambda term will be 0. So, I will start with the negative, and with respect to time this slope will go in the with a positive value, and sometime it will cross only once the t axis. So, once my lambda 2 is negative, my u is positive, as this will be 0, it will switch to negative. So, my switching in the u will be positive to negative when both are negative. So, u is plus 1, then will become minus 1. If lambda 1 is greater than 0, lambda 2 is greater than 0, this means my lambda 1 and lambda 2 both are positive value with respect to t. At t equal to 0, I have the positive value only. So, I have a negative slope of the line as shown in the last figure here. So, once this is positive, your u will be negative, and then this will switch to the positive value. So, this we can see here, if both are positive, then u is minus 1 and then plus 1. This means if both are positive, u is initially minus 1, then switch to plus 1. Both negative, then u will switch from plus 1 to minus 1, as we have seen in this figure representing this case. Lambda 1 positive, lambda 2 negative, I have plus 1, this is representing this case, and lambda 1 negative, lambda 2 positive, u will be minus 1 as represented in this case. So, this basically this will decide the switching, and in a time optimal control system, maximum number of the switching will be n minus 1 is the maximum number of switching, where n is the order of the system. So, we have considered a second order system. So, maximum switching is 1. So, in the one switching, this means I can transfer my any initial state to origin. This we have to show. So, this is the switching we have seen. Now, we will see how this switching can take place. So, for a given system, we have to consider the phase plane trajectory. So, this means my u can switch either to plus 1 or to minus 1. Now, we take if u is 1, then what will be my system? My system is x1 dot t is x2, and x2 dot t is nothing but u. So, x1 dot t is x2t, and x2 dot t is nothing but u. This is my system, a double integral system which we have considered. So, in this case, if you will see, I have x2 dot t, u we have considered as plus 1. So, the solution of this is, so I can simply write my x2 t is nothing but x2 0. So, this is the solution of my second equation. Say this is 1, this means my dx2 by dt equal to 1. So, the solution of this will be t plus x2 0, where x2 0 is nothing but my constant which we are determining. So, the solution this will be t plus x2 0. if I will write my x1 dot t, this is my x2 t, so I can write this as a t plus x2 0. So the solution of this equation will be 1 by 2 t square plus x2 0 t plus x1 0, where x1 0 and x2 0 is nothing but my initial conditions. So this is by evaluating the integration time constant I am writing these values. So from this equation, so I can say this is my equation A, this is my equation B. So I can eliminate t from these two equations. Eliminating t from A and B, I can write x1 t as 1 by 2 x2 t square minus 1 by 2 x2 square 0 plus x1 0, or by rearranging this I can write my equation in terms of x2 square 1 by 2 x2 square t as x1 t minus C1, where C1 we consider as x1 0 minus x2 square 0 by 2. So if I will solve these equation with u equal to plus 1, I will get equation in x1 x2 as half of x2 square as x1 t plus minus C1, where C1 is my constant which will depend upon my initial condition. Similarly, we can solve if u equal to minus 1. So my equations will become x1 t, x1 dot t, this remain x2 t, but x2 dot t is u, which will become now minus 1. So x2 t, the solution of second equation, so the solution of this will give me x2 t as minus t plus x2 0. Substituting x2 in x1 dot t, so x1 dot t is nothing but my t plus x2 0. So the solution of this will become x1 dot t equal to minus 1 by 2 t square plus x2 0 t plus x1 0. So this is the solution of this equation. So the solution of x1 x2 dot t equal to minus 1 is x2 t is minus t plus x2 0, and the solution of x1 t as minus t plus x2 0 is x1 t equal to minus half of t square x2 0 t plus x1 0 t. Let us say this is my C equation, this is D equation. Similarly, eliminating t from C and D, eliminate t from C and D equation, we get a equation in x1 and x2. So, I am directly writing this. I can write this as x2 square t by 2, this is minus x1 t plus C2, and C2 will be x1 0 plus x2 square 0 by 2. So, this will be my another trajectory equation for with u equal to minus 1. Now, if we will make a plot of x1 x2 with u equal to plus 1. So, now if u equal to plus 1 and my x axis is the x1, y axis is the x2, this means I am trying to plot this equation for u equal to plus 1, and I will plot this equation with u equal to minus 1. So, this is nothing but the trajectories with, if u equal to plus 1. So, this is nothing but my x1 x2 trajectory which will move as a parabola. If c equal to 0, this line represents the c equal to 0. If c is greater than 0, my parabola will be on this side, and if c1 is less than 0, my parabola will be on this side, and where the c1 depends upon the value of x1 0 and x2 0. Similarly, for u equal to minus 1, my this equation is for u equal to minus 1, and here again if we will plot the trajectory, this is the reverse parabola I am getting at c2 equal to 0, less than 0, greater than 0. So, my these two equations give me the x1 x2 trajectories in terms of the parabola. Now, if I will draw this two on a same graph, so my whole of this graph will basically cover my initial condition. Initial condition is x1 0 and x2 0. They can exist anywhere in this space, and if you will simply concentrate here, this is the value of my, this is the 0 axis. 0 axis are at this particular point. So, with this means my this whole space, my initial value can exist. Now, I have to see if I have my initial value anywhere in the space, what type of the control I can have. So, let us draw this. Say if this is my space, for u equal to plus 1, I have parabolas like this. I will take only the two case. For u equal to, so these trajectory are spreaded over, so something like this. This will go in this way, in this way. So, this is u equal to plus 1 and this is u equal to minus 1. Suppose my trajectory, initial point exists at this point. This is my x0. It will have the value of the x1 and the value of the x2. So, what should be my switching at this particular point? This means if it is u equal to plus 1, so this means my trajectory will go away from this. So, my control cannot be positive, and if I will apply the u equal to minus 1, my trajectory will move in this way, reach to the switching line here and then move to this way. So, this will be the switching point. So, what we are saying, say now my all these trajectories are spreaded over the throughout the curve with u equal to minus 1 as shown here with the blue line and u equal to minus 1 as shown by the red line. So, and the black line which is here, it shows my switching curve. So, my switching curve is which is driving the state to the origin, and it will drive the state to origin only when, so this lower portion is, this is for u equal to plus 1 and upper portion is for u equal to minus 1. So, if somewhere I am in this region, so means I have to force these initial state to move towards this line. So, this means this will be my positive region. So, this region will be when I will apply my u equal to minus 1. If I will apply the u equal to minus 1 beyond this line, so this means I am forcing my all the trajectory to move towards the switching line. So, this means my all trajectory will move towards this switching line. So, I will apply the u equal to minus 1. So, they will come here and then I will switch to u equal to plus 1. So, they will drive this to the origin. So, this means as we have seen here any trajectory. So, I can say this bold line which is going through the origin, and this is for my u equal to minus 1. And this curve lie on the u equal to plus 1. So, beyond this line, this whole region I have to select that for I will apply u equal to minus 1. If anywhere in this space my initial condition exists, because they will drive this to the switching line and then I am switching my control to bring it to the origin. Similarly, those are in this region, let us say this is my initial condition. So, this means I have to apply the u equal to plus 1 which will drive it to the switching line, and this line here I change my control to minus 1. So, this will drive it to the origin. So, this gamma line which is shown here as a gamma, I can say this is my switching line, region right to the gamma line is for u equal to minus 1 and region left to the gamma line is for my u equal to plus 1. So, here we can see the switching line, this portion is for u equal to minus 1, this portion is for u equal to plus 1. So, when I am in this region, so I am placing u equal to minus 1. So, this means they are driving using this trajectory to my switching line. For u equal to, at the switching line my u will be plus 1 and I will drive it to the origin. So, gamma plus the locus of the initial point which can be transferred into the origin by the control line plus 1, and similarly we define the gamma minus. So, u equal to plus 1 for all initial condition on the gamma plus curve. This means this is my gamma plus curve. So, if my initial condition will lie anywhere on this line, so I have only one control, that is u equal to plus 1. Similarly, if my initial condition lie on this, my only one control u equal to minus 1, if at gamma minus curve u equal to plus 1 and then minus 1 for initial condition on the region R plus. So, which region we are saying R plus? The region, this region R plus is here, or this whole region which is left to the switching line is my R plus region. So, this is in R plus region my control is u equal to plus 1 to drive it, say u equal to plus 1. So, it will drive this to the gamma line and then minus 1 to transfer origin. Another case, this is u equal to for region R minus. So, this should be negative, it is wrongly written here. So, it is minus 1 to plus 1, this just be reverse. So, this means this is my R minus region which I am driving u equal to plus 1 first and then u equal to minus 1 first at the switching line, it is u equal to plus 1 and I will reach to origin. If I am somewhere follow the other path, means suppose my initial condition is this. So, my path also may be u equal to plus 1, then so this is for u equal to plus 1, this is u equal to minus 1 and again u equal to plus 1. So, for let us say for 4 point D, if x 0 at D and my switching is plus 1 minus 1 plus 1. So, this is plus 1 minus 1 plus 1, again I am reaching to the origin, but not in the minimum time. So, my optimal switching is I am in the region R plus. So, it should be simply minus 1 plus 1. So, if I will select minus 1 plus 1, this means from D point I am coming here and reaching to this. So, this will be my optimal switching and this we have to reject. So, in this way we can implement the point region minimum principle to the time optimal control system. So, this was a very simple example. More bigger problem can be solved utilizing this the point region minimum principle. So, at this point we will end our course. Hopefully, you will be benefited by this course. So, your feedback will be required. Thank you very much.